Hello and welcome to our webinar today presented by Dlubal Software. Today we will be working in our finite element analysis and design software RFEM. The topic for today's webinar will be seismic equivalent loads using a response spectrum analysis, again using RFEM. My name is Amy Heilig. I'll be one of the presenters today. I'm located in our Philadelphia, Pennsylvania office. My colleague Stefan Frenzel will also be presenting towards the end of the webinar today and also answering any questions you may have. He's in our Leipzig, Germany office. Just to let you know, you guys can go ahead, show or hide that control panel with that orange arrow if it does seem to get in your way of the modeling or any of the slides. We also want to encourage you to ask questions during the webinar. You can use the chat dialog box down at the bottom, and we will do our best to get to all questions today. If by chance we don't, I'll certainly send you a follow-up email afterwards. With that, I think we can go ahead and get into the content of the webinar. Today we'll be looking at an overview and features of our RF-DYNAM Pro modules. These are add-on modules to our main program, RFEM. We will be utilizing a framework type structure. It's an existing structural system, so we won't be doing much modeling in today's webinar. If you are interested in modeling specifically or more details about this, I would encourage you to go ahead and view some of our previous webinars located on our YouTube site or our website. We'll be performing a natural frequency analysis today in RFEM. Here we'll be importing masses directly from load cases. We'll create a mass combination in accordance to the ASCE7, and then we'll be taking a look at the different natural vibration cases. After this natural frequency analysis, we'll go ahead and perform an equivalent static force analysis. We'll be looking at the definition of a response spectrum directly from the ASCE7. Here we'll go ahead and select our mode shapes that are relevant. And then I want to take a look at a couple different cases, one without accidental torsion and one with accidental torsion according to the ASCE7. And then we'll go ahead and export all of our load cases and combinations back into RFEM so that we can use concurrently with the other load cases such as dead load, live load, snow load. So as I mentioned, we'll be utilizing the dynamic modules in RFEM. And we have 3 DYNAM Pro modules. The first one is RF-DYNAM Pro Natural Vibrations. This is essentially always needed. This will perform your natural frequencies and mode shapes for any members, surfaces, and solids in your model. Here you can import masses from load cases, you can create mass combinations, and in addition you can manually define additional masses, not only at nodes, but also on members, surfaces, lines. We can also include any initial conditions such as axial forces, stiffness modifications, and a little bit more, and I'll be showing that today as well. Then we have our RF-DYNAM Pro Force Vibrations. This is for a time history analysis, and it's for a multimodal, multi-point response spectrum analysis. So essentially you can perform a response spectrum analysis differently throughout a single structure. We won't be using this module today. We did do a previous webinar walking and running across a pedestrian bridge that utilized this module, and it was a time history analysis. So again, this is on our YouTube channel or on our website. Today we'll actually be using the RF-DYNAM Pro equivalent loads. This is a multimodal response spectrum analysis where we will generate equivalent static forces. We'll go ahead and create load cases and result combinations and export them back into RFEM to again use with our other load cases. So with that, I think that we can go ahead and get right into RFEM. So as I mentioned, we have an existing structure here. It's nothing too complicated, just some typical steel shapes according to the AISC, and then we have a couple slab elements for concrete. Then I went ahead and I added a few load cases here. We have dead load, live load, and snow load. So with our dead load, they're just simple area loads on our surface elements here, and then I used our load generator to go ahead and apply this area load on each member. We can right-click and display separately to see how those loads are being attributed to the members. This is all before solving as well. Then for live loads, same sort of concept, but I have only applied them to the first level here. And then lastly, we have snow load. Again, same concept, but it is applied only to the roof level. So with that, I think that we can jump into our RF-DYNAM Pro add-on module. Over here on the left-hand side in the Project Navigator is our long list of add-on modules. And just a little tip here, you can right-click on any of these modules and tick them to add them to your favorites so that they'll go ahead and show up at the top here. Or else you can also go up here to add-on modules, and they're categorized a little bit better here. And you'll notice we have Dynamic and Dynamic Pro. So this will go ahead and launch the add-on module. This dialog box is essentially all that entails the add-on module. A little note here as well that all of these modules essentially have the same interface. So whether you're doing steel design, concrete design per the ACI or any other international code, dynamics, for the most part, most of these modules have the same interface and the same workflow. So it's very user-friendly no matter which model or module you're in, that it won't look completely strange when you launch it, but more similar, so to speak. And as I mentioned before, we have our 3 dynamics add-on modules here. Here is natural vibrations, here's force vibrations, and here's equivalent load. So it all just depends on what's activated on your license. We'll go ahead and start with the natural vibrations. And we want to go ahead and click this mass combinations checkbox here. And you'll notice that the mass combinations tab popped up when I did that. Then we'll move into defining our mass cases. So initially we want to give a description for our first mass case, and here we can just type in dead load, and we want to define the mass case type. We'll leave this as permanent. A lot of these other categories are for international codes, so for the ASCE, we'll go ahead and just leave all of these as permanent. Now we need to define which masses are a part of this mass case. So our first option here is from the self-weight of structure. The second option is from force components of our load case, which you can see the previously defined load cases that I have here, dead load, live load, snow load from RFEM. Had I defined any load combinations, those would be available here, but I didn't define any, so that's why this drop-down box is empty. So for our case, we're going to go ahead and leave this as dead load, but what I do want to do is to uncheck this from self-weight of structure. The reason for this is I've already accounted for self-weight in my load case 1 here. So if I have this checked as well, it will count for it twice, which is not what we want to do. We can also manually define additional masses here. This is nodes, lines, members, and surfaces, and again, all of these tabs popped up as we check these on. So for nodal masses, you can go ahead and list additional nodes, define your additional masses here, as well as mass moments of inertia used for torsional modes. We have line masses, member masses, surface masses. It's quite user-friendly to use as well. You can just click in this cell, and then you can actually just define a surface graphically. So you don't necessarily need to know the number of the surface, but rather you can do everything graphically. If we were to define some additional masses, that total would be shown here in the additional masses at. For our case, we're not going to define any additional masses, but what you can do is you can go ahead and calculate the mass quickly, and the program will actually sum up all of your total masses being used for this particular mass case. We can also get the center of total mass in the X, Y, and Z coordinates. If we click on the details button here, it's just a few more in-depth topics I just want to bring up quickly. We have our mass conversion type. So right now the default is set to Z components of loads. So any loads that we have in the positive or negative direction in the Z global direction, those will be considered for this mass case. We have Z components of loads in direction of gravity. So essentially this would be any loads defined in the negative Z direction are used only. And then we have the full loads as mass. So this would be if you had loads defined in the X, the Y direction, the Z direction, all of those would be considered for your mass conversion. The same that we added masses, we also have the option to neglect masses here. If I check that checkbox and go into this dialog box, it looks familiar that we were just looking at, but here you can actually choose to neglect any masses along these elements in the translational or rotational direction. And then we have our acceleration of gravity, which is of course used to convert forces to mass. So we want to go ahead and create a couple more mass cases. This one we'll go ahead and give the mass description live load. We want to uncheck the self-weight and choose live load as the load case. And then lastly, we have snow load. Again, unchecking self-weight, and then we'll go ahead and choose snow load from our load case. Okay, so we have our 3 mass cases here. Now, the next thing that we want to do is to go ahead and create a mass combination. I want to go back to the PowerPoint here because ASCE 7 in section 12.7.2 addresses mass considerations. Essentially, the code tells us that we need to include all masses above the base for dead load. If we have any areas that are used for live load storage, we need to include 25% of this. And then if we have any snow loads that are greater than 30 PSF, then we need to include 20% of this. So with these considerations, if we go back into the model, we certainly want to use all 3 of these mass cases. And I can quickly add them to the mass cases to be considered for this mass combination. I can also give the mass combination a description. You can have multiple mass combinations here. For our case, we're only going to have one, so there's no need to give it a description. But what we do want to do is to go ahead and change these factors. So live load, as we just saw, we want it to be 0.25 and snow load as 0.2. So now we have our first mass combination in accordance with the ASCE 7. So now with that said, I think that we can go ahead and move into our natural vibration cases. With our natural vibration cases, same as with the mass combinations, you can create multiple natural vibration cases. Give it a description. For our case, we will only have one, so there's no need to give it a specific description. Since we don't know anything about this structure, it's asking us the number of lowest eigenvalues to calculate. We can go ahead and start at 30. I think this is an adequate number to go ahead and solve for when we initially don't know anything. The next question is the acting masses. So we can choose our mass cases here, or better yet, we have our mass combination that we created according to the ASCE. Now it's asking us in what directions do we want to consider for this natural vibration analysis. I'm going to go ahead and explain these X, Y, and Z directions as well as the X, Y, and Z rotations concurrently with our calculation parameters. So if I click on this calculation parameters tab, I can see that there are 4 types of mass matrices. The first is the diagonal matrix. So with this one, all masses are lumped to FE nodes. So not just our nodes that are available in our model, but actually every FE mesh point. Only translational masses are considered. So this is X, Y, and Z. There will be no torsional modes. So essentially, even if you have these checked or unchecked, it really doesn't matter when you have this diagonal matrix chosen because the program will ignore all torsional modes. However, the exception to that is when we define a mass moment of inertia for nodes. And that was back here in our mass case. If we additionally define masses at nodes, remember we had this option to go ahead and add in a mass moment of inertia here. So for this option, this will actually be considered for our torsional modes despite us choosing a diagonal matrix. I'm going to go ahead and uncheck this since we are not considering that. For the diagonal matrix with torsional elements, this again is where all mass is lumped to the FE nodes. Here translation and rotation are both considered. However, with rotation, it depends on the member or surface element's longitudinal direction. So for instance, we have this beam here running in the global y direction. So masses about the y-axis will be considered. For this column here, it's running in the global z direction, so masses about the z direction will be considered. The rotation is nothing more than their distance to the center of mass combined with the mass of the elements. So that is for this second option here. The consistent matrix is actually where masses are not lumped to FE elements, but rather shape functions are used to distribute the mass. And then we have our unit matrix where the mass at each FE point is set to 1 pound. Both of these are a little bit more complicated, especially the unit matrix. It's more of a mathematical approach for a numerical analysis. So default is diagonal matrix, and we'll go ahead and stick with that. Now the scaling of mode shapes. These top 3 here are just essentially for viewing purposes back in RFEM. We have the square root of the sum of the squares here for our eigenmodes, and we will set that equal to 1. We can set the max of the translational modes equal to 1, or the max of the translational or rotational modes equal to 1. We'll go ahead and leave it as the default here. This other option here, it's actually used internally for a response spectrum analysis and time history despite our selection of these 3. So keep that in mind that this is used internally anyway. This is where modal masses are set to 1 pound for each eigenvalue. The method for solving eigenvalue problems. So for this category, this is more of performance rather than accuracy. All are considered accurate. The question is, what is the size of your structure? So with the root of the characteristic polynomial, this is ideal for small systems. Here, all eigenvalues are calculated. The Lancos is the default, and this is an iterative method to determine the lowest eigenvalues. This is good for medium to large systems. Now we have the subspace iteration and the ICG iteration. This is where only a few eigenvalues are determined, and this is best for large structures, but keep in mind that this is going to be a much longer solve time than when we're using these first 2. The edit FE mesh settings, this just links back to our FE mesh back in RFEM. So this is for the whole program. What do we define our target length for the FE mesh? Initial conditions here, if we go ahead and click on activate, then we can import axial forces, stiffness modifications, and extra options from our load cases. And if I go ahead and exit out of our ADA module and I go back into RFEM, here's where I define my original load cases in RFEM: dead load, live load, snow load. So looking at the calculation parameters for dead load, I have a couple options here. Modify stiffness and extra options. Again, these additional tabs appear at the top. If I go to modify stiffness, you can see here that I now have the ability to modify the stiffness for materials and cross sections, supports, releases. If I go to extra options, there's a few more other details here that we can go ahead and apply, such as initial strain from another load case or combination. We can import a stiffness from RF concrete. So those are what we are referring to when we go back into this Dynam Pro module, and we can activate the initial conditions here. Keep in mind that these are initial conditions. They're considered for the first iteration only because this is a linear dynamic analysis. We'll go ahead and check that off. And back in the natural vibration case, we will just consider X, Y, and Z, although it doesn't matter if we have these checked because we are running the diagonal matrix. So now I can hit OK and calculate. What the program's doing now is just determining the analysis for the natural vibration case. Okay, so if we are back now into RFEM, and you'll notice here that we have our first mode shape displayed, and we can go ahead and move up this table so we can see it a little bit better. And here's our 30 mode shapes that we solved for. We can go ahead and scroll through these mode shapes, and you'll notice that the program is updating according to the graphical interface up here, according to which mode shape we're in. We can also click in the table according to the mode shapes, and everything is updating graphically. In the table is our actual information from our natural vibration case, and we can pull open the natural vibration case here from our drop down if we had solved for more than one, but of course we only solved for one, so that's the only one available at this time. So here you can get information such as the eigenvalue, the angular frequency, and natural period. Then we have some other options just to kind of separate out the different information according to node, for example. So here we have node number 1, and then we have all 30 mode shapes. Then we have node number 2, and you'll also notice that the program has a big red arrow according to which node we're looking at. So it's especially useful when you're in these long tables and you have no idea where you're at graphically here. So as we switch to the different lines on the table, you'll notice that the arrow goes ahead and updates as well. We have mode shapes by member, so here's member number 1, and we have all 30 mode shapes. We have mode shapes by surface. We only have 2 surfaces, but what the program's doing is including every mesh point and then 30 mode shapes for every mesh point. So you can imagine that these tables can get rather long, but again, as we're clicking through them, the program is moving my red arrow, showing me exactly where I'm at. If we take a look at mode shapes by mesh node, we can get the displacements and the rotations according to each FE mesh point in the structure. Masses and mesh points is important because if we scroll down to the very bottom of this table, there's actually a summation here. This is the total mass being applied to this structure. You'll notice here in the X, Y, and Z, they're all 3 the same because we didn't differentiate any masses for the 3 separate directions. So it makes sense that they're all the same values. Equivalent modal mass factors. So here we have our effective modal mass. This is essentially our mass that's being used for this specific mode. And then we have our effective modal mass factors. So this is your mass participation. This is nothing more than our effective modal mass divided by that total mass being used in each direction. So I think that we can see here that for mode shape number 1, we have a mass participation of 92%. So I think it's pretty safe to say that this is our dominant mode for our Y direction. If we look down here at mode shape 14, we have 93% in the X direction. Again, it's probably safe to say that this is our dominant mode looking at all of these other mass participation factors. We can scroll down to the bottom and see a summation. We have a total of 93% and 98.9%. Keep in mind that the ASCE 7 requires at least 90% mass participation. So if you're not reaching this 90% down here with this sum, then you need to make some changes to your model. Maybe that's solving for more eigenvalues, or maybe you need to take into account your mass cases, and if you have some heavy machinery, you can go ahead and add in some separate masses back in the DYNAM Pro add-on module. Okay, so now that we have that, I think that we can go ahead and go back to our DYNAM Pro, and you can see here that there's just a quick link while we have our panel still open here. And sorry, back here in this first tab, we have the equivalent loads checkbox. So what this is doing, this is launching the add-on module for equivalent loads. And the only thing that happens is just a couple more tabs will pop up here. So our natural vibration cases, they're still relevant for everything that we just solved for. But now we actually want to go ahead and define a response spectra. Here, again, we can give it a description, but for our case, we will only have one response spectra, so we don't necessarily need to put in a description now. Here we have all of the different standards according to, we have the NBC 2005 here, we have several IBC codes, the Euro code. For our case, we'll be in the IBC 2012, and then, sorry, ASCE 7-10. Here's all of our applicable information directly from the ASCE 7. What's also great about this is that we have our table here. And as we scroll through the table, you'll notice down at the bottom that my graph of my response spectra is actually showing me where I'm at as I click through this table. You have the ability to change your time step if you'd like, to whatever you prefer. So for us also, I wanted to take note that this is the case for most of the tables throughout RFEM and the add-on modules. We have a direct link here to Microsoft Excel. So you don't have to worry about copying and pasting and headers and everything of that sort, but just simply click this button and all of this information will be exported directly to Excel. You also have the ability here to have a user-defined response spectra. Here you'll define period and acceleration, and it will go ahead and graph as you enter in these points. Again, you have the option to import from Excel here as well, and then export once you have some values shown in here. So for us, we'll go ahead and stick with the IBC 2012. I want to go ahead and change my design category to 2. Maybe my site class to D, my spectral response accelerations, which you can move these columns over since they are a little bit longer than what this column's allowing, but we'll leave these as 50% of G. My response modification factor, let's go ahead and change this to 2.0. So now we have our updated response spectra here. Now if I click in the dynamic load case, we'll go ahead and create our first dynamic load case. For this one, we do want to give it a description, and we'll call this one without torsion. And here you'll notice that these options are grayed out. This is for our force vibrations add-on module. So if we did go ahead and activate that, then we would be able to do a time history or a response spectra analysis. But instead, we will be using the equivalent static force analysis to perform a response spectrum. We have our natural vibration case to choose from here. Again, we only have one. If we had more than one, then that would be available in this drop-down. Then we have our equivalent force analysis. So which directions do we want to consider here? I'm going to go ahead and check the X, Y, and the Z. Now there are stipulations in the ASCE 7 that do allow you to neglect the Z direction in a response spectrum analysis. For us, I'm going to go ahead and leave this checked just for the sake of our example, but we will see that the Z direction really doesn't have much influence anyway. This factor I will get back to later on in the webinar, but for right now, we're just going to go ahead and leave this as 1. Now we can also rotate these equivalent loads that will be produced in the X, Y, and Z direction about the global Z axis. So this is useful if maybe you have a structure that's not directly in the X, Y, and Z axis, but maybe more at a skew. So here you can actually rotate your forces about the global Z axis as well with the structure. So that's useful, so you don't necessarily have to be in these direct coordinates. Right now we'll go ahead and leave the accidental torsion off, and then we want to go ahead and generate load cases here. So this is all of the information that will be exported back into RFEM and considered for analysis. So the first one that we have checked here are load cases for all modal shapes. We certainly want to export our modes back into RFEM as load cases. After we do that, we want to further go ahead and produce a result combinations from all of these modes. And how the program will do this will be according to the SRSS rule, which I'll show you in our next slide. Then from here, as soon as we get our results in the X, Y, and Z direction, we don't necessarily know how to apply them to the structure. Do we apply them all at once? Do we apply them only one at a time in each orthogonal direction? And the code, of course, addresses this. And in the appendix, it suggests that we use the 130 rule. This would apply 100% in the X direction and 30% in the other 2 directions. Then we'll go ahead and apply 100% in the Y direction and 30% in the others, and same for Z. So we'll go ahead and stick with this 130 rule as well. Then lastly, we have our mode shapes here. So this is just all of our information from our natural vibration case. If we hadn't solved for a natural vibration case yet, this would be empty in here, and we would have to calculate mode shapes with this button right here. So you'll notice right now that we have all of our mode shapes selected, but as we saw before, there's several modal mass factors that are just 0 for these modes. So they're really not beneficial for our analysis. So rather than selecting all, I can unselect here and I can individually uncheck each of these that are not being used. Or an even quicker option, especially when you have a lot of modes that you solve for, is you can select all but then deselect modes with an effective modal mass factor less than 0.05. So now you'll notice that I only have my mode shape 1 and 14 selected, and the other modes that are not so relevant are unselected. I take a look here at my effective modal mass factor sum. I'm still above 90%, which is what the code requires. So for this situation, this is fine to neglect all of these under 0.05. If we were under 90% here, then maybe we would need to decrease this number to 0.03, 0.02 until we reach at least 90% here. Again, for our case, this seems to be adequate. So you'll also notice here that as I click on the different modes, I'm getting my period as well as the corresponding acceleration with red lines down here. So again, just beneficial for seeing where you're at exactly on this response spectra. So I think with that, we can go ahead and click OK and calculate. So now what the program's doing is just determining the equivalent loads in the program. You can see it's pretty quick for calculating that dynamic analysis. What I want to show you here is that let's go ahead and start with our drop down here. So now we have some mode shapes here for our load cases, and we also have result combinations. Let me go ahead and clarify a little bit about what exactly was exported from RF-DYNAM Pro. So we're back now into our main program RFEM, but we utilized RF-DYNAM Pro to export our equivalent loads for our seismic analysis. You'll notice here in our load cases, we have our dead load, live load, snow load. This is just what was already defined before performing our seismic analysis. But now we have some mode shapes, and we have kind of a special case here for this structure because we had those two dominant modes, mode shape 1 and 14, for both, or for all of our X, Y, and Z directions. This is pretty rare. Usually you're going to have several mode shapes for all directions in order to go ahead and reach that 90%. But for our case, you know, we do have these dominant modes here, so this is what we chose to utilize in our response spectrum analysis. Then if we go ahead and go to our result combinations, and here is where we have our result envelope, and this is just taking the mode shapes and combining them according to the SRSS rule. And with this, let me go back to our slide here, and let me show you exactly how these equivalent loads are calculated. It looks a little bit intimidating at first, but realistically, if you break it down, it's not too complicated. So for each line here, we have an excitation direction. So this would be excitation in the X, the Y, and the Z. Then for each direction, we have a force in the X, the Y, the Z. We have our participation factor here. We have our mode shapes. Then we have the acceleration from the response spectra that we defined as a function of our period. And then we have our masses. Then for each mode, we have this, this output of our equivalent loads, but we need to somehow combine all the modes for a single direction, and that's where the SRSS rule comes into play. So for each mode, like this is a single mode here, this is another mode, we're going to combine according to the SRSS rule, and this is just the square root, sum of the squares. We also have the option to combine according to the SRSS rule, but with the preserve sign option. This is default in the program, but you certainly can check it off. This would take into account if we had a negative moment with a positive axial force. Well, all of those sign options will be taken into account with this equation here. So going back to our model, this is what the SRSS rule is doing here in our X, Y, and Z direction. So you can see here under calculation parameters, we have the SRSS rule. This is just implemented into the program, and then we have the option to preserve signs or to uncheck that, but we want to leave that checked for now. Now again, keep this in mind that typically, which for our next case, you will have more than one mode shape. We just had an ideal structure here where we had one dominant mode shape that reached the 90%, so the SRSS rule is really not too applicable here. Now we have our result envelope according to the 130 rule. So this is what I was explaining earlier, that we have now our forces in the X, Y, and Z, but how exactly do we apply them to the structure? Again, do we apply them all at once? Maybe we apply each one individually, and the ASCE addresses this and suggests that we apply 100% in the X direction while we have 30% in the Y and Z. Then we have 100% in the Y with 30% in the other directions, and then 100% in the Z. So the program automatically calculates all of this for you. So with that said, I want to go back into my add-on modules, Dynam Pro. And now we want to go ahead and create a dynamic load case. And what I can do is I can just copy my selected dynamic load case here so that all of my settings from previously will be remembered for this copied case. However, I'm going to go ahead and title this one with torsion. Now, if we're looking at our equivalent force analysis, we want to check this checkbox here, consider accidental torsion actions. Going back to the PowerPoint, in ASCE 7, section 12842. Accidental torsion is for assumed displacement of the center of mass. And what the code calls for is for 5% of the length in the X direction and 5% of the length in the Y direction to be considered as eccentricity when applying our forces. So our moment is derived simply from those forces that are being applied to our structure multiplied by this eccentricity. So back in our model, we need to define what these eccentricities are. In our X direction, we have 51 feet for our structure length. So therefore, 5% would be 30.6 inches. In our Y direction, we have 16.4 feet. So 5% of that is 9.84 inches. Everything else will be kept the same. The result combination, I'm just going to increase this to 10 so that I don't override my dynamic load case 1. You know, mode shapes, everything is still applicable, so I can just hit OK and calculate. So now the program is going to calculate dynamic load case number 2. The other thing I want to show you as well after we solve is that in our results here, so we already went through the natural vibrations case 1, but we now have a dynamic load case 1 and 2 here, and we have all of our different mode shapes. The advantage here is to again scroll to the bottom, and we can actually see, let me go ahead and go back to dead load or dynamic load case 1. We scroll to the bottom here, we can actually see the equivalent sums that are being added up in each direction here. So that's what these are essentially used for, these tables. So something to keep in mind there. And we can click on all mode shapes. You can view one mode shape at a time. If we're under all mode shapes, then you know, we can go ahead and see the sum that's being applied. Z direction, again, is very small, so it's not very applicable, but our X and our Y directions, 115 kips, and then in the X direction, we have 117 kips. So again, this is for all mode shapes, which is only 1 in 14, but you can see the total sum of our equivalent forces that are calculated. So now that we've calculated with accidental torsion, I just want to compare that to without torsion. if you take a look at our load cases now, we now have several more that were calculated here. We have torsion in the plus and minus direction for X, Y, and Z. So I want to show you guys here, if we choose one of these torsion cases, and I'm displaying my load. So it looks certainly not so nice when we're looking at it here, but if we scroll in a bit, then we can see that these are FE points within the model. So this is a member element here. We have an FE point here. We have three forces in the X, Y, and Z direction. And then now, to take into account our accidental torsion, we have this moment acting on this FE point. If I choose the minus torsion, it will look exactly the same, except for our moment is reversed with signage. So you can see that this is how the program is applying these equivalent loads at each FE element in the program. Going back into our load cases and combinations, sorry, let me go ahead and, there we go. Going back into our load cases and combinations, let's go to our result combination. So here you can see dynamic load case 1. We've already been through all of this. This is without accidental torsion. But dynamic load case 2 now includes torsion. If we look at our result envelope X, now we can actually use the sum of squares, or sorry, the SRSS rule for the two different mode shapes, because we now have torsion. And we can go ahead and expand this a little bit. We now have torsion in the in the positive and negative direction. So the program is using the SRSS rule to go ahead and combine our mode shapes to create a result envelope for our X direction, our Y direction, and our Z direction. Then our 130 rule is used again. Again, for each result envelope here, you can see the components that make up this specific result envelope. And we can tell here by our factors that 100% is being applied in the Y direction and 30% in the other two directions. So that's just the difference between accidental torsion and not applying accidental torsion. So I want to do one more thing, and that's just kind of clean up the model a bit according to the ASCE 7. So if I go back into my add-on modules, Dynam Pro, and I go to my dynamic load case here without torsion, I'm just going to go ahead and uncheck this to solve. I just want to stick with our with torsion now, considering our eccentricity. I'm going to move this back down to result combination 1. And then I'm going to go ahead and click OK and calculate. So now the program needs to calculate the natural vibration case and the dynamic load case for all of my entries there. So you can see here that we're back to our natural vibration case, but we also have our dynamic load case with torsion. And again, I want to revisit this load cases and combinations. So going back to the PowerPoint, we now have these E loads. This is an ASCE 7. Everybody's familiar with this. These are our simple load combinations according to LRFD and ASD. The program with our Dynam Pro add-on modules has calculated these E loads, but now we need to somehow combine them with our dead load, our live load, our snow load. We also have our ASD combinations here. For us, we'll go ahead and stick with the LRFD load combination 5. Also a note here in the code, section 12.4, it talks about redundancy factors and overstrength factors. This is something that you will want to take a look at, and if you meet the requirements for either redundancy factors or overstrength factors, the code actually calls for the replacement of load combinations according to these sections here. So sections 2 are now not relevant, and you will go ahead and replace with the load combination set forth in section 12.4. Again, for us, we'll go ahead and stick with LRFD load combination 5 here. So back in the model, again, as I mentioned, we already have our earthquake loads, but I want to create a new result case here. And for the description, this is just from my knowledge to kind of know what result combination I'm running. I'm just going to type in what the LRFD equation 5 here. And we clearly see that we have dead load, live load, and snow load here. So I just want to add all three of these load cases here. I need to adjust my factors a little bit to 1.2. My snow load will be 0.2. And then now I need to somehow take into account this earthquake load. So we have our earthquake loads according to the 130 rule, but the question is, do we need to create a result combination with this first result earthquake loads, then another one including the second one, and another one including the third, since we don't know what the worst case is? But the answer is actually that we can use the program to help us here. If I go ahead and select all of these 130 rules, there's a button here called Add Selected with Or. If I click this, and I'm going to quickly change this to permanent, although it doesn't impact our results, but you'll notice here that now for our result envelopes 130, they are set to variable within group 1. So the program will actually cycle through dead load, live load, snow load plus this first result combination, then go back dead load, live load, snow load plus the second, and determine which is our worst case scenario. So that's kind of useful that we don't have to define a whole bunch of load combinations here, but rather the program will do it for us. So now that we have that, we actually have this result combination available here, and I can just simply run it as I would any other load combination in the program. So as you would run a load case, a load combination, or anything else in RFEM, we now have our results according to this specific result combination. Here we can take a look at our global deformations, we can take a look at our members, and maybe we want to look at the normal forces, the shear forces. We can also take a look at our surfaces. If I turn this into wireframe, we can look at the contours according to our moments within the surfaces, stresses, anything else. So for that, it essentially sums up how to combine the equivalent loads with our other load cases. Now, the other thing that we quickly need to talk about, and that would be the story shear and drift. Base shear and story shear are important topics in the ASCE 7. So we want to take a look at a quick way of how to actually gather that story shear and base shear information. The other thing is our drift information. Here I'll just utilize our tables and our nodes to go ahead and define what we want to look at with our drift. So back in the model, if I take a look at this and I go ahead and select these two columns over here, and I'm just holding down my control button, I just drag it and drop it here. It's asking me, do I want to clear my results? That's fine. So now I just have this column kind of floating out here in space. And what I want to do with this is to select everything. I'm going to right click, edit my member, and then under member type, the typical type is beam, but we have several other options here, of course. But one of the options is a result beam. And if I further clarify some properties here, I can go ahead and define what exactly entails in my result beam. This is going to integrate stresses and forces, and what I'm going to choose is from listed include objects. And what it will do, it will integrate all stresses and forces for all my surfaces, all my solids, even though that's irrelevant in this case since we don't have any solids, and all my members. So if I go ahead and hit OK, and you'll notice that all of our results were lost when we kind of modified the model here. So what I first need to do is to solve for my dynamic load case. Again, this is cycling through the natural vibration case and the dynamic load case to come up with those equivalent loads that we've already specified. I also want to go ahead and run this result combination according to the ASCE 7, equation 5, and the program will quickly run through this. Now, if we check our members and we turn on our shear in the local Y, you'll notice that this beam actually has some values on it. If I right-click and turn on my local axis system, the local Y shear corresponds to the global Y. So what this means is that this is actually our base shear in the global Y direction. Our first story shear is nothing more than 116 minus 66. And then our top story shear is 66. We can go ahead and switch it to shear in the Z direction. Again, this is just under members. And here this corresponds with our global X direction. Our base shear is 115, and then we have our first level shear at 113 minus 60, and then our top level shear is 60. And this is all in KIPS, and if you forget any of the information, you can go ahead and look up here in this table. It will give you which load case you're running, or sorry, which result combination, as well as the internal forces and the units. So why this is important is, or sorry, let me go back to the model to show you one more thing. The other thing I wanted to show you real quickly is story drift. So let's go to wireframe here, and under display, I want to go ahead and show my display here. And this, as you can see, is giving us a deflected shape of our model. If I go here, I've actually already done this, but you can create views, user-defined views of what you want to see in your results. So I've selected just these top columns here, so you can see that this is the only deflected shape here, these yellow lines. And then I've also done the same for the bottom columns. And graphically, we'll get the max based on this selection as well. So you can see here that we have a deflection here of 4 inches. So maybe we certainly want to consider this column for our story drift. If we go down here to our nodes deformations, and I select these 3 nodes here, you'll notice that they highlight according to the table. So that's kind of nice. You don't need to sift through the entire table to understand which node you're looking at here, but rather it'll go ahead and highlight it here. But I can also go ahead and use this button, show selected objects only. And now only my node numbers 32, 33, and 34 are shown. I can go ahead and show my numbering here to understand where I'm at, and then I can get information about my story drift. So the reason why base shear is important quickly is that according to ASCE section 12.9, it states that when our modal base shear is greater than 85% of our calculated base shear. Our modal base shear is what was calculated from our response spectrum analysis. So going back to the program, if we take a look at our results and we go back to our members and we take a look at the shear values here, here's our base shear that we're looking at for our modal base shear. If that's greater than 85% of our calculated V, calculated V comes from the equivalent lateral force procedure. So that's just spelled out directly in the code of how to calculate that. Then if this equation is met, we need to multiply our forces by this particular factor here. And the question is, where do we use this factor in the program? And that's where I said I'll get back to these factors in the Dynam Pro module. So opening up Dynam Pro real quickly, if we take a look at our dynamic load case, we have our factor here that we can go ahead and apply that 0.85 times our modal base shear over our calculated base shear. So you can also take into account redundancy factors here and overstrength factors. So that's where you're essentially going to be multiplying your response spectrum by these factors, which will in turn multiply your equivalent lateral forces by this factor. And then the last consideration is p-delta effects. ASCE 7 in section 12.9 refers to section 12.8, which is in the equivalent lateral force procedure, says that we can neglect p-delta when our stability coefficient is less than 0.1. The stability coefficient is just this equation here directly from the code. We can get most of this information from RFEM, or if some of the factors are, of course, you can find those directly in the code. For our model today, our stability coefficient is 0.04, so therefore we do not need to consider p-delta. With that, I quickly want to turn it over to my colleague Stefan, who will be going over a few more key points in our next release of RFEM.
Okay, hello. So, here we have, of course, new features for the new module RF-DYNAM Pro. The first is the QCQ rule for the equivalent forces procedure. So that means we have now a complete quadratic combination in the next customer version of RFEM or RF-DYNAM Pro. And with this rule, is it now possible to consider damping effects in the superposition of the result. Yeah, therefore we have two options in the new RF-DYNAM Pro or in RFEM, of course. The first one is that we can consider this new rule in DYNAM Pro directly, or we can create earthquake load cases manually and can use them afterwards in the result combination and can choose there the QCQ rule. For the QCQ rule, we have here now the option to consider the layers damping or a relay damping, and the values which we need just for this are the damping values and of course the angular frequency of the used modes. Yeah. I just want to show you how to work with these new options here in the program. Therefore I will switch to RFEM, and here you can see, of course, a small model which is nearly the same like Amy's before. And here in the DYNAM Pro module we have now the option in the dynamic load case to consider this CQC rule. Yes, of course. Here for this rule we just have to check in, and if we want to use this rule we get a new tab where we can put in the damping. So the damping here, of course, the relay damping coefficients or a layer damping, or of course we can give layer damping differentially for each mode. So if we choose this one, for example, we can choose for every mode a known damping. So normally we just use the layer damping here. I will take just 5%. I think that's enough for this small example. And now we just have to calculate it. And we will see now, of course, the results with layer damping, which is here in the result envelope. We have here, of course, we have to calculate it again because it's an envelope of the results. So we need the results from the load cases, and therefore we see now here the deflection. Here we have now also the option to edit a result combination, and in this result combination we have here our calculation parameters. In this calculation parameters we see now here that the CQC rule is used, yeah, because we created these result combinations in DYNAM Pro and they were exported to RFEM afterwards. Here you have, of course, an info. You need, of course, earthquake load cases if you want to use this CQC rule. In the load cases you can also we have the load cases. In these load cases here you have, of course, some new options, and here you see of course the angular frequency and the last damping which is used. The angular frequency is here used from the DYNAM Pro module, and here you don't have an option to change something, because if you want to use it as a user-defined load case, then you have to change at first the general data, so the options, and here you can of course use RF-DYNAM Pro, use CQC rule and less damping, and if you create now directly a new load case, which should be here of course an earthquake load case, then you have the option to change of course the angular frequency, and the damping is here of course used with 0.05, so 5%, and yeah, this was possible also to change in the basic settings of the module. Another new option is the combination of signed results. So signed results using dominant mode is it called, or we call it like this, because here yeah, that's a new type of combination. So that's therefore you can use also the SRSS rule or the CQC rule, and if you use it, you have then the option to use the signs of the prevalent eigenmode and to take these signs for the whole result. So that means that you don't get two signs for each result combination. Yeah, with this rule is it now possible to get a unique result. Yeah, so I will show this also in RFEM, and therefore I have to switch back to RFEM, and maybe I show you at first the result of the result combination which we created here, the result envelope in X direction. And here you see always two results, yeah, one in the X direction and one in minus X direction. This is caused by the SRSS rule or by this quadratic combination, because you will lose your signs and you will get two results. And if you now want to change that, you have to go back in the result combination. So for example, for this result combination, and you can edit this result combination in the calculation parameters and have now here the new option according to load case or combination, and can choose directly here a mode shape. From this mode shapes, the signs will be used and will taken, yeah, these signs will be taken then for the result at the end. So normally you have here to choose a dominant mode or eigenmode, and therefore we go back at first in the DYNAM Pro module, and here in the DYNAM Pro module we have to look at first in the dynamic load cases, and of course to have a look in the mode shapes. Here for this example you can see we have two mode shapes which are useful for us in the X and the Y direction, and of course we have two mode shapes which are useful in the X direction to get our 90%. So here you have to choose of course normally the dominant mode shape to use it then afterwards in the result combination. So I would here take the mode shape 1 for the Y direction and the mode shape 14 for the X direction. So if we know this, then we can go back in the result combination. Here, for example, the result combination for the X direction, can go on edit and can choose here now the load case for the X direction. So that should be load case 6, that was mode shape 14, and can choose them, and afterwards we get just one result. And yeah, that's the advantage now is here that we just have one result out of the dynamic combination or out of the dynamic calculation, which gives us more efficient results when we want to design afterwards the whole structure. For example, in steel, or if we have a concrete structure, then we have just one result, and yeah, that's more efficient in the end. Yeah. We can do it also, of course, for the Y direction here. So we just have to edit the load, the calculation parameter. We have just to select the result combination, and then we have to add here the load case 1, which is mode shape 1 in Y direction, and choose it here also. Then we calculate this load combination, this result combination, and we get, of course, just one result for the whole structure. So Amy, I'm ready with it. So back.
Okay, thanks, Stefan. So yeah, that's just a few of the features coming up in our next release in the next few months. So in summary, I just want to go ahead and suggest that everyone visit our website, dlubal.com. We did go ahead and redo the entire website at the beginning of the year. So you haven't visited it in a while. It does have a completely new look. We, of course, have several social media blogs, videos, newsletters, and we have several events and conferences that we'll be attending in the coming year. So those are listed on our website as well. Here's our email, info-us@dlubal.com. Phone number here in Philadelphia is 267-702-2815. We'll certainly have more upcoming webinars on our website, email, newsletters, so keep a lookout for those, and you can register directly on our website as well. It's under the support and learning and then webinars. So I know that probably many of you also would like PDH credit for today. If you can just go ahead and send me a quick email, info-us@dlubal.com, to let me know that you would like a certificate. I will be more than happy to go ahead and issue that and send it back to you. And with that, that is the conclusion of the webinar today. Feel free to get in touch with us with any comments or questions, and thank you everyone for your attendance today.